I'm a senior, and I'm a member of the Frame and Drivetrain group.
I'm Luke Camp. I'm also a senior, and I'm a member of the Advanced CAD and Task subgroup.
Clay Collinger. I'm a junior, and I'm part of the Frame and Composite subgroup.
I'm Grant Williams. I'm a sophomore, and I'm a member of the Advanced CAD Task and Telemetry subgroup.
All right, so to start off, if you get the next slide, we have we have an animation of different various components of the rover, and we're going to speak over them. This animation was made by student Luke Camp. So to start off, the material that the rover is made out of is carbon fiber 3K twill. The length is 98 inches, the width is 52 inches, and it weighs 129 pounds. The driver configuration is one seat behind the other with both facing forward. So the frame is configured of two foam halves that were wrapped in carbon fiber. This consisted of 7 layers of carbon fiber, which varied in carbon fiber tape layers, which were 3-inch wide tape, which was 3-inch wide carbon fiber tape that was wrapped around foam, and then 4 full layers of carbon fiber. More layers were applied to areas that have high stress and in the past have proven to be more weak, such as joints. This frame was also vacuum bagged to prevent sharp edges and to make sure that epoxy is spread evenly throughout the frame.
So to meet our volume constraint of the 5x5x5 cube, the rover has to fold in half. So to do this, the original plan was to use a sleeve that would go over both halves of the rover and then using 2 hitch pins on either half to keep it in place. However, the group ran into a problem where there was excess space between the sleeve and the frame. So to fix this, originally the plan was to take urethane pads and stick them in this excess space. However, this ended up causing friction that made it difficult to assemble and disassemble the rover quickly. To solve this, we have finally come to the solution of using urethane to adhere the sleeve to the back half of the frame permanently, and then using a single hitch pin that will keep it in place on the front half.
This year, each wheel consists of 1 internal mounting flange and 2 carbon fiber halves, which are glued together and then sandwiched by 2 external flanges. And then tread is wrapped around the circumference of the wheel. Each halves are made off of MDF molds, which are cut on our CNC. And these halves are made of 6 layers of carbon fiber, and then we add triangles to the center to reinforce where the plates are. In the past, we've had problems with the strength of the metal, so we add triangles there to reinforce it. Each wheel has 2 different types of flanges. There are 2 external, which is an 8-inch thick aluminum, and then the internal one is a 1/2-inch thick aluminum as well. And the diameters slightly overlap to reduce pressure, which this also helps relieve the stress on the wheel hub, so the center of the wheel does not snap. Running along the outside, we also have our tread, which is a polyurethane mix, poured onto an HDPE mold, which we design and cut ourselves. And then once cured, this takes about 18 hours. Each piece is attached to the outside of the wheel using rapid fuse and painter's tape, which is later removed. Due to all the prep, cure, and dry times, the total process takes about 4 days per wheel.
So this year's drivetrain follows a similar train of thought to last year's, which is a single speed system involving both rear wheels, with the front driver controlling the back left wheel and the back driver controlling the back right wheel. We chose this system this year because it's proven reliable in years past to get the rover over flat stretches of land and navigate through obstacles with relative ease. The major difference this year, though, is that instead of drilling holes through our frame to attach our axle, we now have plates that hold the axle in place on the back of the frame. These plates were custom made and their purpose is mainly to keep the axle straight so that when we're driving it doesn't bend. And this year, the assembly of these plates has gone very well to keep them in place, as well as adjust them on the fly with minute adjustments. We did run into some problems when we vacuum bagged the frame and it came out with some wrinkles on the carbon fiber. And our first thought was to sand down these wrinkles and then put the plates over when they wouldn't fit. However, the design of the plates actually allows us to grind down the 1/4 inch side a little bit so that it will fit over the wrinkles even after they're sanded down a bit. And this allowed us to fit the plates on and adjust them as we needed to keep the axle straight on those rear wheels. Lastly, the other problem we ran into is with the chain that goes from the front to the back. And when we saw it initially, it would run over the frame and under it. But we decided when it fitted awkwardly over the frame and didn't have a lot of slack that we had to drill a hole through the frame instead to tension it. Like the drivetrain, this year's steering is also similar to last year, involving the Ackerman steering principle in geometry, which allows the wheels to turn at different angles and not slip when we're turning. The tie rod is connected to both of the wheel boxes, which are both also as well connected to the handles which the driver uses to steer the rover. What's very significant about this design is the use of 2 leaf springs, which are the curved pieces of carbon fiber attached to the front main beam. These hold the wheels in place and provide strength and flexibility at the same time. That's because there's 12 layers of carbon fiber or of fiberglass sandwiched in the center between 6 layers of carbon fiber on each side. And these allow the frame to bend but also be strong at the same time with that configuration. We ran a lot of tests to figure this out, involving different amounts of curve of the leaf springs and different configuration of the layers. But we figured out that the best configuration would be able to hold 90 pounds per spring, including the weight of the driver and the front of the rover.
Okay, so this next animation, well, first here is a quick photo of the actual rover in person. And then the next animation that we have basically goes over the requirements and the rover passing them, such as the 12-inch lowest point, which shows here that our rover fits over 18 inches from the lowest point. It also covers the 5x5x5 cube. So in addition to what I was talking about with the sleeve earlier, the sleeve must come for the 2 halves to come apart. The chain must come off of the transfer axle because the sleeve is now permanently attached to the back half. So one part of our team that is significant is that each member has to take a mastery test that does go over the guidebook. That way each member fully understands the requirements such as the 5x5x5 cube, other constraints, as well as the obstacles and tasks that would normally happen during the race. So here is our matrix. So the team uses a matrix in order to verify the completion of requirements from NASA's System Engineering Handbook, as well as document when and where these requirements were completed. Next slide, please. So here's some other photos of requirements, such as the seat belts, as well as driver PPE, including helmets, glasses, long sleeves, etc. On the left side, you can see our free body diagram, which basically proves that the rover can fit the 30-degree angle incline environment. This shows that this composite rover does fit a 50-degree angle incline, and this can be told by the center of mass still being in the green part of the diagram. And here are some of our drawings. This is just a sample. The majority of our drawings are in the ORR report, and if there's any questions about this, they are welcome at the end of the presentation.
So this year, Parish chose to once again pursue the 3D printed design challenge for Task 5. And our design was pretty similar to last year, barring 2 major improvements. One of these was the square hex tube design, which allowed us to get a reliable print without sacrificing any of the stability or strength of our 3D printed parts. And the other big improvement was the telescoping action of it, because last year we had trouble mounting such a long pole. So we decided this year that we would make it telescoping, so that way we wouldn't sacrifice any of the driver's reach while actually performing the task, but make it easier to store on the rover. And then on this slide here, we have some pictures of our other task equipment. For the mission performance predictions, sadly we won't be racing this year, but based on what we know of the course and how we've done previously, and some of the testing we've done with this rover, here are the tasks and the obstacles that we think we could have done on day 1 and day 2, with 81 points that we think would have gotten on day 1 and 94 on day 2.
So to just give a quick update, since we submitted the ORR report, we have been able to test drive the rover once, and a few things have come from that test drive. So to start off, the position that the steering handles were originally in was way too far forward for the tie rod to be able to move. So we had to bend the steering handles backwards, which, as you can see from the photo, made driving really awkward and was not an optimal position for the steering handles. So in order to combat this, the steering handles were moved up further so that they could be at the downward angle without making it awkward for the driver or making steering difficult. And then additionally, because of the way that the front seat is positioned, there was additional stress on each side since it's only connected in the middle. So the seat did crack. So you can see additional reinforcements that were made to the seat in the slide as well. And then here are just some photos of frame construction. And then if you go to the next slide, as well as a few photos of the completed rover. That was our test drive, and then just a little bit of collaboration with the team members. And then for STEM engagement, I had the pleasure of being a Blair Fellow this year, so I had the opportunity to perform various experiments with pre-K through second graders and teach them about STEM and how it related to their other classes and what they can learn through experiment. So by doing this with various classes, I was able to reach around 140 students. And then 2 of our team members also were able to make a blog post encouraging young women to participate in STEM. And then finally, the team created a video which highlighted members of the rover team and their experiences in middle school STEM classes and encouraged middle schoolers to sign up for those courses. And as that was shown to pretty much the whole middle school, it reached 350 students. Thank you guys so much for your time. We would love to take any questions.
All right, great job, guys. Good report, good presentation, the animation, that was fun. Great job on all that. So I have a question, and it can be for 2 of you. Maybe 2 of you that didn't say anything might be good, but it doesn't matter, any 2. From start in the fall to almost finished now, what is the one thing that you're going to take away from this challenge that you are going to carry on either in when you go to college or in your other classes? What is that one thing that you're like, wow, okay, yeah, I got this?
I would say the biggest thing, at least for me, is to face adversity head on and not give up. Because there's been many times throughout this challenge, especially because this is our first year building a rover out of this material, that we faced adversity or things didn't work right or something broke right as we're finishing. And there's been times where you just wanted to sit down and give up because it's just hard. And it's just the biggest lesson that I've learned is to push through and not give up even when stuff goes very wrong.
Good. Anyone else?
I think I'd add on to that as well, and say that one of the big lessons for me this year as a senior was being able to adapt to change. When we designed this whole thing, we kind of expected things to go a certain way, be able to drill a hole here and make sure that things lined up. But when it came to actually assembling this rover, for the steering, I know that instead of like where we figured out how to line up the Ackerman in CAD, in reality, we actually had to use string to line up the bolts to the back of the axle to figure out where we had to cut plates. And so that was fun for me in teaching Clay and my subgroup how to do that, really made me realize that the most important thing I can learn from this course is being able to adapt.
Awesome. Great job, guys. Scott, do you have any questions for the team, sir?
I do. You guys have a very sleek, good-looking design, and I see in the back where you have the chain guards around the sprockets in the back, and you've got a long expansion of chain. Have you looked at having chain tensioning and the distance that you have from frame to ground? You show it's 18 inches. Is the chain lower? Do you still have that minimum clearance from your chain to the ground?
I think I can answer this as well. To the chain clearance question, those leaf springs that are designed as the suspension were intentionally curved really a lot. They were curved a lot so that the wheels would be the frame would sit pretty high on the wheels. And that was intentional so that that chain would kind of be at a pretty high distance to the ground, not just to the pedals, but also like the chain that sits kind of right next to those leaf springs, so that would sit pretty high over the ground and wouldn't hit any obstacles. And to tensioning the chain, we've looked into using derailleurs and derailleur mounts as well to have that chain run through. We've also 3D printed chain guides on the rover and on the sprockets to make sure that they don't slip off.
You've got a good looking design. I like the carbon fiber frame. That looks good. That's all.
All right, thank you, Scott. Dennis, do you have any questions for the team, sir?
Oh, a couple, I think. So the rover is beautiful. I mean, I love the rover. Some of the most gorgeous rovers I've ever seen have been all composite, and finished like that. This is the first one I've seen that had curvature to it. I mean, it had like style. That's kind of cool. For the stem, did you worry or have the opportunity to worry about measuring the effectiveness of the STEM engagements that you had? It's become kind of a mantra of people and I'm not an educator in that sense, professional educator, but it's become a mantra for them to be able to quantify the interest or the knowledge of students that you might interact with before you've interacted with them and after you've interacted with them. Have you improved their interest? Have you improved their knowledge over whatever the subject matter was? It kind of goes along with lesson plans, that kind of thing, which you wouldn't necessarily have a formal lesson plan for STEM engagement, but something where you can quantify the effect, whether you've had a significant influence or not.
So for the Blair Fellow program, whenever I go over to classes, I'm a part of so I help the teacher in her lesson plans. So the STEM already happens. It's like a part of the classes, a part of the curriculum. So I'm not really sure that there's a way to quantify the impact, but I do get to go over there and help them with their lesson plan and help them execute certain designs that will help them make sense of certain lessons and kind of have a hands-on component to learning in that sense.
Yeah, for formal education, which I guess that you're dipping into like that, that's where the exams come in, where you're actually testing them on the material that you hopefully conveyed effectively. I wouldn't hesitate to document what you're doing into the report. So the report that you have now has a lot of information, but you got, after you submitted it here, you no longer have the constraints on size or page count or anything. Include what you've done. Take credit for what you've done. Inform students that come after you of what what has been accomplished, all of you, on the kind of stuff that you've done. I was also worried about your rover coming apart and coming back together and how you're managing the belt. I saw a little bit about how you were doing that. It's a requirement that you maintain the 12 inches between the belt and the ground. It's just smart, you really ought to maintain that. I think I'll leave the geeky engineering stuff. I'm just a scientist. I'm going to leave that to Sean. So I'm done.
Just a scientist. Stop it. All right, Sean, do you have any questions for the team?
Yes, I do. Great presentation, by the way. The animations are pretty incredible. I'm very impressed with those. And the completed rover here, as I'm looking at it, I'm really impressed with it. You have the resources available to accomplish something like that. I really want to amplify what Dr. Gallagher was just mentioning on adding more stuff to this report, even after this is all over, because you can all present this to future employers, college applications. I mean, I imagine I'm like just beating the bush on this and that you've already been told this by your advisors, but this is really good stuff for prospective career options. Even if you're just in high school, it doesn't matter. So a lot of this work, you're going to be excelling really well if you pursue university. There's some teams that you can go on there to keep on this type of thing. I have some questions about the leaf springs. Have you done a long-term fatigue testing on the leaf spring?
We have not been able to do a long-term fatigue testing. We did short-term weight tests and weight drops, but we never tested anything for more than 2 or 3 minutes.
Okay. I would maybe make like just a small piece and just flex it over and over and over and just make sure that you're not having any cracks in the epoxy or the resin. So I would hate for it to start after, bending a piece of metal a bunch of times, it eventually breaks. Everything work hardens and work destroys itself basically. So just keep an eye on that. But I imagine the 8 minutes that it's on the track, it wouldn't encounter a problem. But as far as the chain, as Scott had mentioned, I would highly recommend putting an idler of some sorts on that chain system in the middle. It would help you with preventing that chain from hopping off that front gear. If you're hitting a very big bump, you probably experienced that if you've jumped a bicycle and the chain just flies off the front gear. Have you researched belt drive systems? I feel like a thicker belt drive system would be more adequate for this design. Have you researched that?
I'm not sure if we researched, I'm not particularly a part of this group, but we've used a belt drive system in the past on some of our steel rovers, and we found it to be pretty good. But I think for the sprocket kind of base through drivetrains we're using on this one, the chain made the most sense. But I think the belts have worked well for us in the past. I think that could be a good thing to look into next year.
Great. Yeah, you might even find, I would definitely do some serious, try to push as hard as you can as somebody's holding the rover, just to make sure so usually the longer the chain you have, the more it will stretch, which becomes an issue at that point, and it can come off the cog. Although belts do stretch as well, but they tend to bound back quicker. The mating surfaces between the carbon fiber and between each carbon fiber piece, is that for you have bolts and such? Do you have any extra material there to help prevent breaking, or is there a metal or washers or anything like that? An example would be how the leaf spring is attached to the frame in the front.
Yeah, there are washers in between the bolts and the leaf spring on both the top and bottom.
Okay, great.
And then in the leaf springs, at the parts where the bolts are, so in the middle and then the edges, we layered 12 extra layers of carbon fiber on each side because we were worried about them snapping at the steering point. So on those points, there's actually 36 layers instead of 24 of composite materials.
Great. I'm glad you're thinking about, yeah, you either have to add in extra material or you have to add in some sort of metal substrate to counter those forces that are on those high stress areas. So great on that. The only other issue I might see is, although it depends on how strong you are, the front crank and how it's mounted on the front there. Are you worried about that possibly breaking off, or is it the same thing you had just mentioned, where you have extra substrate there?
We did think about that. We actually made a whole mock pedal arm. It was the back pedal arm, but we cut out a foam and wrapped a pedal arm, and then we hung, I believe it was 85 pounds from just the bracket shell to make sure that the carbon fiber wouldn't come off there. And then we do have a few extra layers of carbon fiber over the top there on the bottom bracket shell.
Perfect, great. You've obviously thought of all the things that I'm asking, and it's great. Great design. I feel really proud. If you're a senior, if you're going to a university, pursue another rover team there. I would like to see some of this work carry on, and then again, documentation so other high school students can carry this legacy on. It's great. We really hope to see you all next year as well. Thank you so much.
All right, guys. Like they said, great job, and so on and so forth. You've done amazing. I know you know that April 7th is the deadline for the video submission, and then to have April 16th on your calendar for the awards ceremony. We will send out emails closer to time so that you're aware of what platform we're going to use and what time it will be. There's a lot of coordinating going on right now, so trying to get everybody's calendars and stuff at the same time is tough. But we will let you know, obviously, closer to time. So with that being said, enjoy the rest of your day, and thank you so much for presenting to us. We'll see you later.
Thank you.
Thank you.
Bye, Jen.